Okay, great. So we've talked about function handles, we've talked about functions, and we've played around with f0 as an example of a function. Now let's try to apply f0 to something a little more engineering applicable. Okay, so we're going to look at our projectile motion example problem and see how f0 can help us with that problem. So first of all, you're going to need to grab some of your function files. So go ahead and pause the video for a second and go find initial chords, initial velocity components, quadratic, and landing distance. And if you grab those from homework 4 or any homework after that, you should be fine. And then I have also provided you with a function called DistanceDiscrep. And be sure that you have that in your current folder, and we'll talk about what that function does in a second. Okay, so once you've got all those functions rounded up, we will take a look at the DistanceDiscrep function. So first notice that I have defined a few things here in the lecture 16 note script. So we've got x target equals 0.8 meters. For the d values, we're just going to use 0, 0, 0 to keep things simple in this example. And then the initial velocity, we will use a value of 3.5. Alright, now let's go ahead and take a look at the DistanceDiscrep function. Okay, so here it is. The name of the function is DistanceDiscrep. It has 4 inputs: theta, that's the launch angle, the d values as a vector, the initial velocity v0, and then x target, so the distance of the target that we're trying to hit. Okay, and the output of the function is dist, and we'll have to see what that is. So inside the function, what happens is that we call our landing distance function, pass it d, v0, and theta, and it will kindly give us xland. Okay. And then we're going to compute dist, the output variable. That's going to be equal to x target minus xland. Now note that there's no absolute value, so dist can be either positive or negative, depending on if x target is larger than or smaller than xland. Okay, and the significance of dist is that when dist is 0, that means that we're hitting the target, right? Because x target is equal to xland. So if we can find angles theta for which dist is 0, then we'll know what launch angle to use to hit the target. Okay, great. So let's go back out to the lecture 16 notes script, where there's already code to create a vector of theta values from 0 to 90. And then we've called the DistanceDiscrep function and passed in theta and our defined values of d, v0, and x target, and we are assigning the output of that function to dist. So let's go ahead and plot dist versus theta. Alright, so let's open a new figure, and then we'll say plot. On the horizontal axis, we're going to want the theta values, and on the vertical axis, the dist values. Okay, so let's go ahead and run that. So the values range from, the dist value ranges from 0.8 at a launch angle of 0 degrees, down to negative 0.4 something at 45 degrees, and then back up to 0.8 at 90 degrees. Alright, and because we're using 0, 0, 0 for our d values, this plot is symmetric about 45 degrees. Okay, so let's think about where dist is 0. Okay, so again, this gives us the angles that will let us hit the target. So here's 0, so that looks about 20 something degrees, and then if we come over here again to find the other 0, that looks like 70 something degrees. So that's kind of what we're looking at for the angles that would hit the target, and we're going to have MATLAB help us find exactly what those angles are using the F0 function.